the Lunavust theory in the case of all spherical varieties. So now let me tell about the theory in the general case. We fix an homogeneous space G mod H, and we suppose that it's very spherical. And then we will classify so the G mod H embeddings in terms of colored files. So the first things we can define is the lattice M. So we can't define it directly as for all spherical varieties are so the lattice generated by some characters, but here we use the fact that if we look at this space, then it gives a lattice, and we define M as this lattice. So for each element F here, it corresponds to a weight. So this space is the eigenvector under the action of B, and the eigenvalue is a character. So we have a lattice here, and so the rank of M can be used to define the rank of G mod H. Okay, so we also have N, so the dual of M. And we also have so so I also define colors. So I define the set of colors as a set of bistable, irreducible divisor of G mod H. And as before, we will have a map from D to N, which to divisor D sends so the map from this space to Z, which associates so the degree of zero endpoints along the divisors D. Okay. And in fact, we can extend this to the set of G-stable irreducible divisor of any G mod H embedding X. Okay. So maybe just note here that, so remark, that if D is G-stable, then sigma of so the map. So sigma of how can I yes? So VD, so the variation so from C G mod H to Z, so to F associate the zeros, the degrees of zeros and poles of along D. So this is a variation, and since D is G-stable, this will be a variation which is G invariant. So a variation is G invariant means that for all G we have the variation applied to G times F acting on F is the same as the variation of F. So for all G in the group G. Okay. And for the colors, we will obtain a variation which is a B invariant, in fact. Okay, so remember that to define a colored cone associated to a simple embedding, we choose a cone generated by the image of the color and also elements of n. And there's element of n where the image of G-stable divisor. So we can only choose G-stable elements of n which come from a G invariant variation. For all spherical varieties, G invariant variation can have an image everywhere in n, but not for spherical variety in general. So that's why we consider the cone of variation. So we call it the cone of variation. Of G mod H, which is by definition so the set of so the set of image of the valuation in so image of G invariant valuation, so in n. So we have a G invariant valuation here, so we restrict to only to the eigenvector under the action of B, and we can quotient we can do the quotient by C star, and we obtain a point of n. And so it's maybe the R cone generated by so I look the cone in so it's a cone in NR. And so first result is that nu is a convex polyhedral cone. Okay. So this is the first difference between the general case and the orospherical case. So this is a new things. So all I said this was the same for orospherical light. So now we can, so if X is a G mod H embedding, we can associate it a colored fan, so as the same way as as before. So we don't use for the moment that we have this new here, but to have a bijection, we have to restrict the definition of colored cones to so maybe definition, so colored cones. So we have C, F. So with F a set of colors, and C generated by so the image of the element of F. So for D in F, and elements, so finitely many elements of not only n but n intersected with the valuation cone. And we have the same condition as before. That was, so there's no colors which image 0, and there's no line in C. So these points are the same as the last definition. So maybe I draw a picture. So we have a cone, nu, here, and then we have some. So we have also image of colors. Here we can have also a color here, here. Well, so we have some potential colors, and then we have to take a cone, which is generated by elements in this cone, and some of the colors. So we can take one color here. Sorry. So we take this color. So you can take a cone generated by this color and an element of. So here we take an element of n. So here we have a colored cone with one color, and the other color can't be colored, and this must be a color of the cone because it's outside the valuation cone. So we have to choose it as a color. So we can't erase these colors. Okay. And so another example is so we can also take a cone like this. So with or without this color, with or without this color. So this will be also a colored cone. And so by this way, okay. So so we can't have. Yes, there's another condition. So we can't also have this cone. So this cone is not allowed. So this is not allowed. So we have to have at least one element in U. So here I must say that there exists. So the interior of the cone intersect nu non-trivially. Okay, and then we have the same condition as before. So we have this condition also more, and this condition also, which is new. So we have two new conditions. So we can't choose elements in N outside the valuation cone, and the cone must intersect the valuation cone in its interior. Okay, so we can't also have this. This also is not allowed. So it must intersect in the interior of the cone.
Simple example of non-holospherical.
Yes, so for example, wonderful variety or symmetric varieties are not holospherical. So I will will give the example after this, and we will see an example with the same group and one holospherical and one symmetric. So we will see this, and I will explain. So in this example, why there's we can't choose. So there's the variation cone is not all the space. Okay, so now, yes.
This is definition of what? A colored cone.
Of a colored cone. So a colored cone CF is some colors. so a subset of the color of G mod H, and a cone generated by the image of the color and elements of N intersected with the validation cone, so that the cone intersects the validation cone in the interior, and then the points here are that so the image of a color is non-zero and there's no line in C. So we don't want to have a half plane, for example.
This is the generalization of the definition again.
Yes, this is the generalization of. Yeah. So for maybe yes, I can just note that nu is all the space if and only if G mod H is orospherical. So if the variation cone is all the space, then you can erase this because so n intersected with nr as n, and you can also you can also erase this condition because so when I take the interior of C, it's the interior, the relative interior of C. So it's so the interior of an half plane is just an half line in the plane is just so it's the half line minus 0. So it's the relative interior of C. So it's not. So a cone has always an interior non-trivial. Okay, so this is a generalization, and then you can generalize a colored face. So here the only difference is that so here for the yellow example, so you have only so 1, 2, 3. So you have 3 faces, 3 colored faces. So the first one is all so it's CF itself. The second one is this half line. So the half line with so this one. So it's the second line, and the third one is the point 0. So we have three faces in that case. We can't have the half line with the color because we don't have this condition. And then we can define, as before, a colored fan, which will be a colored, so a finite set of colored cones with this definition. Okay. So now we have, so I just want to say what can be generalized, so what result can be generalized. So the first result is that, so the theorem of Luna and Wust is also true. So there is a G mod H embedding quotiented by isomorphism of embedding is in 1 to 1, so is in bijection with the colored fan. Okay, and we also have that complete is equivalent to be complete here. So colored fan here is complete if for all x is in the variation cone, there exists CF such that x is in C. So we just, maybe I draw a picture. So we have the variation cone here, and then so we have some colors, maybe here, and when I can take this cone, for example, and this cone, So we have a fan with two maximal cone on their faces. So here it's a color, and this is a complete fan. So this is complete. So it does not cover all the space, but it covers the valuation cone. So then we also have a bijection between G orbits of X and the colored face for the elements of the fan. And so what was also done yesterday? Okay. So we also then we have no smoothness criterion. But we have a local structure, so we know the local structure of spherical varieties. So it means that so for all y G closed orbit, closed G orbit, so there exists, and for all for all elements in Y, there exists an affine B-stable an open open set containing the open subvariety containing Y. So that's why subvariety. So I denote it by U. So it's an open neighborhood of Y, which is B stable and affine, and not affine. Sorry. Excuse me. So it's not necessarily affine, and so of Y such that so U is equals to some unipotent radical of some parabolic subgroup, and so Y is G mod P prime, and this is the parabolic subgroup times Z, and Z is spherical, and wondering. Yes. So it was affine. Sorry, because Z is affine. Okay. So we can describe locally. So the X as a product of a unipotent radical times an affine spherical variety, which is smaller than X. And it's spherical, so under the action of a Levy subgroup of P prime. So in general, if you want to prove that a given embedding is smooth, we have to look. So we look at this affine spherical variety, and if we start with a projective variety, then Z will contain a fixed point, and then it will be embedded in G modules and so L modules. So if we denote L, and well, we can then check if Z is smooth or not when we know that it's in a G model. But there's no general smooth criterion because we can't generalize what we have done for our spherical varieties. So this is a difference. Another difference is.
So what is B-stable for you?
Sorry?
For you?
B-stable subvariety, so open subvariety or open neighborhood of Y. So another small difference is that so an expression of the anti-canonical bundle, it's the sum of the xi plus the sum of coefficient so of the color. So D is in D, but these coefficients are not. So there's no explicit expression of this coefficient. We only know that they are greater than 1, but not explicit formula. Okay. So the description of the local structure and also this expression of anti-canonical bundle is due to Briand. This is also due to Briand. And another result which is due to Briand is the criterion of Cartier, Ampol, also globally generated divisor. And this criterion is almost the same as the criterion I gave yesterday. So I didn't write it here.
In this statement, is P prime a parabolic group?
Yes, P prime is a parabolic.
So when you say closed G orbit, when Y is closed G orbit,
no, it's not necessarily parabolic. Sorry. It will be parabolic if X is complete, so it's projective. But it's not necessarily parabolic. So it's parabolic only if. Sorry.
So this is just now a symbol.
So it's closed G orbit in in X. Yeah.
Just to some subgroup.
Yeah, some subgroup. Yes. Yeah, I denoted by P prime because I often consider only projective varieties. So well, yes. Yes, so sorry. So it also works if X is not projective, so we also have this result. So in that case, P prime is not parabolic. Okay, so we can generalize all almost all results we add for all spherical varieties. In fact, all these results were first proved in the general case and not for our spherical case. Okay. So then I want to give an example. So we take G equals SO3. So in fact, SO3 is P is the same as the PSL2. And so I look at the C3 with the natural action of SO3. So if we want to look at C3 as a module under PSL2, we have to to look at the action of PSL2 on on the 2 by 2 matrix by conjugations. By conjugation, and then this will decompose into C plus C3, where C is C times identity, and C3 is the set of matrices of the form A minus A and B, C. Okay. And so the action of PSL2 on this C3 is the same as the action of SO3 in this. But I prefer to consider SO3 because it will be simpler to explain which variety I consider. So, for example, in SO3, so we have a Q, a quadratic form. So an SO3 invariant. And so I denote also the bilinear symmetric form by this bracket. And now, so I can, so we have Q, which goes from C3 to C, and I can define two affine varieties as follows. So X0 will be so the inverse image of 0, and X1 will be the inverse image of 1. Okay. So if I choose now, so I choose a basis E1, E0, E minus 1. So basis of C3 such that EI and EJ is equal to 1 if I equals minus J and 0 if not. Yes. So then Q corresponds to the matrix with 1, 1, 1, 0, 0, 0, 0, 0. So in this basis, Q is correspond to this matrix. Okay. So I choose this basis, and then I can look at F1, F0, and F minus 0, the dual basis. So I can express now the regular function of x0 and x1 as follows. So C of x0 will be so C of f1, f0, and f minus 1 quotiented by so the equation of q of x equals 0, and this is in this basis, this is f1 f minus 1 plus f0 square equals 0. So I constanted by the ideal generated by this polynomial. And we have the same with x1, but we quotient by f1 plus f1 times f minus 1 plus f0 square minus 1. Okay. So now I take Boris group B as the stabilizer in G of E1, and So fact is that f minus 1 is an eigenvector. So under the action of B, B eigenvector of weight 2 omega alpha, which is can be seen as a map from B to C star, and a matrix Bij we associate. So B is triangular matrices, and we associate B11, which is B33 minus 1. That is okay. And why we have 2 here? It's because so I already said that for PSL2, omega alpha is not defined, so it's not a character of the torus here, because the center. So the center is minus 1, and if we apply omega alpha to this center, it gives minus 1, so it gives something different from 1, so we can't quotient by the center. And PSL2 is SL2 quotiented by the center. Okay, so that's why we have 2 omega alpha. Okay, so now in both cases, if we look at so in both cases, if we look at M, so which is the regular function of x1 or x0, so xi. And in quasi-invariant by B. If we look at this, so we will see that in fact in this, so this is only the set of so the sum of C f minus 1 at the power d for d greater than 0. So in fact M is exactly so Z times 2 omega alpha. So this is true in both cases. And in fact, in particular, it implies that x0 and x1 are spherical, because here we have no multiplicity. So up to a scalar, we have only one. So it's in Z. Sorry, we have only one eigenvector for one weight. So we have no multiplicity, and this is equivalent for affine spherical affine variety to say that the variety are spherical. Okay. So we have 2 spherical varieties with the same lattice, generated by 2 omega alpha, so it's spherical and of rank 1, because the lattice is of rank 1. So now let me consider x0. So for x0, it's very simple, because we have the decomposition into the degree of the function, because here the ideal is an homogeneous ideal. So we can look at the parts of the regular function of given degree, so quotiented by f1, f minus 2 minus plus f0 square, and of degree d. Okay. So of degree d, sorry? This fact? Yes. So it says that if you compute f minus 1 of so b of some x, it will be so it's by definition f minus 1 of b minus 1 acts on x, and it will be 2 omega alpha times b times f of x for all b in the broad subgroup and all x in x0 or x so in C3 if we want. In fact, so it's true. So that's what I mean by B eigenvector. So it acts. So B acts with a weight 2 omega alpha. Why this? So it's okay. So well, yeah. So you can compute this thing. So you can all compute explicitly, and you will obtain that. So here you have B11 or B33 minus 1. So and why I denote it by 2 omega alpha? It's because it's 2 times the fundamental weight of SL2. But I don't want to explain how to go from SO3 to SL2 because so you can compute and explain so you can explain the isomorphism between PSL2 and SO3 by formulas, but so you have formulas, and it will tell you that if in SL2 you have omega alpha, which gives the first terms in the diagonal, then in SO3 so 2 omega alpha, so the first term of the diagonal will be 2 omega alpha. So I don't do the computation, but so if you want to do it, you can do it. Okay. So well, maybe I'll take the degree here. Okay. Okay. So you just look at function of a given degree, and you quotient by the idea. Sorry? 2 times? Yes. Yes. Yes, so there's 2 times everywhere. Thank you. Okay. So we have this decomposition, and in fact this is so this is SO3 stable. And okay, yes. So this is stable. So in particular, this is a SO3 module. And so in degree 1, for example, we obtain C3, which is the simple SO3 module for 2 omega alpha. Okay, and so what I wanted to do is yes. So maybe I just said that for this example, so there is a one color given by the equation f minus 1 of x equals 0. So in fact, it's the line CE1 in x0. So we have only one color, so one bistable divisor in this surface. And its image is just given, so the image is just given by 0 on poles of such function. So here along the divisor, so here we just have so the dual of, so we will have that sigma of, so I denote it by D, one color D. So sigma D of 2 omega alpha will be equals to 1 because we have this equation. So then we have sigma D is equals to alpha dual mod U, mod 2. So if I represent this, so we have a lattice. So 0 to omega alpha, and so this is M, and then we have 0, and this is alpha dual mod 2, and etc. This is M. And this is the image of sigma D. So alpha is the unique simple root of SO3 and SL2. Okay. So now I can define two G-stable valuation by this fact. The first one will be so to F we associate the minimal degree. So here we have a graduation, and to the second variation will be to F I associate the minus the maximal degree. And if we restrict this to only the function to this space, so to the function f minus 1 at 1 power, we will see that the image of this variation in n is alpha change mod 2, and this as image minus alpha dual mod 2. So in that case, we have G stable, G invariant, sorry. So we have G invariant variation with image in one side and also in the other side. And so we prove that in that case, nu is all the line. So it's R. So in particular, we have x0 is all spherical. Sorry?
H in this case is
H is no, H in that case is the kernel of 2 omega alpha in B. So it's yeah. So yes, yeah. For SO3 is the unipotent. Yes. Yes, yes. So now let me do for x1. So for x1, we don't have a graduation like this. And if we take new G invariant variation, then we will have that nu. So we want to compute nu of 2f1 f minus 1 plus f0 square. So this will be the same as nu of 1, and this is 0 by definition of variation. So the variation on constants are always 0. And also it's G invariant, so since nu is G invariant, the variation of f1 must be the same as the variation of f0 and the same as the variation of s minus 1, because letting act G on f1, f0, and f minus 1, we can have the other from each one. We can have the others. So all variations are the same for all this function, and then so we apply the axiom of variation. So we have the variation of a sum is less than it's more than the minimum of the variation of the terms. So f1, f minus 1. So we can't erase the constant because it doesn't matter. And nu of f0 square. And this is by the other axiom, it's nu of f1 plus nu of f minus 1. And so it's equal to it's equal to 2 times nu of f minus 1, for example. So in particular, we have proved that nu of a minus 1 is less than 0. So if we look at this picture, so we will have that nu of f minus 1 is negative. So it will say that the image of nu must be in the negative part of n. So it means that this is the variation cone. So in this example, the variation cone is the half line, so of negative elements. So we can also compute the colors. So we have 2 colors corresponding to f minus 1 equals 0 as before. So so f minus 1 of x equals to 0 implies that f0 square equals to 0 to 1, sorry. So it implies that so we have two components. So f0 square of x f0 of x equals 1 or minus 1. So that's why we have 2 colors. But the image of the color are the same because in fact it's only defined by the same equation with f minus 1. So in that case we will have 2 colors, d plus and d minus, which have the same image, alpha 2 square, which is equals to sigma d minus and equals to sigma d plus. So this is an example where we have 2 colors at the same place. And also an example of not all spherical variety, because we have a variation cone which is not all the space. Is there a question about this example? No? So maybe I just take some remarks on this example. So first remark is that x1 is symmetric. So I didn't define yet what is symmetric. I will define it this afternoon. So it just says, in fact, it just said that x1, well, we can solve that X1 has one orbit, so it's an homogeneous space, and in that case it's SO3 mod, I don't want to, SO2. So, and SO2 is the fixed point of some variation, of some evolution, fixed point of some evolution of SO3. So you can take this as definition if you want. Okay, and so another remark is that, so maybe let's this. So another remark is, so here we compute SO3 mod SO2, and we can also consider SO3 mod the normalizer in SO3 of SO2. And we will add another spherical, it's also spherical, and in fact it's also symmetric. And we will have another homogeneous spherical space where the M is the same, N is the same, nu is the same, the image of the color is the same, but in that case we have only one color, and with the same image. So all is the same, excepted that we have one color instead of two in that example. So another remark is, so we can embed the X1 into and with an open into a quadric of dimension 2, seen in P of C3. Is it true? P of C plus C3. Okay. So we have the open orbit here, so which corresponds to 1 and x. So this is, so the open orbit is is this one. So this is isomorphic to X1 inside it, and so we take the completion of this open orbit inside this, and we obtain a quadric of dimension 2. And if we look at this one, which I call X2, then X2 will be also embedded in this space. No. So X2, sorry, will be in fact embedded in P of C3, which is P2, and with an open. And last remark is for X0, so we can also have a completion of X0 also in P of C plus C3. And here we will see that in fact it's a cone. So if we take the closure inside, it will be a cone over a quadric of dimension 1 in P of C3, so in P2. So in particular, it's singular at so X0 was already singular, so we just put a divisor at the infinity, and we can so we have so 0 alpha dual, and so this X0 corresponds to the fan, the colored fan consisting of the half line here, on the half line here with the color. So this is x0 bar. And if we look at x0, in fact, we add only this part. So we add only this half line as a colored fan. So this was a colored fan associated to alpha. So maybe I should take color. So this is the fan. This is the fan and with the color. And this is the fan with the color. And if we blow up the point 1 0, so in this space, or in x0 bar, then we will have the fan consisting of the two half line, but without the color. So here we have the color, but we don't color the color. Two projective embedding. So this one is I don't know if this one is with or without the color, so I don't remember. Well, so we can describe all these things. So I hope it helps you to understand the theory. And, so there's two examples of rank 1. So one is orospherical, the other is not orospherical. In fact, it's symmetric. So we have to. Yes. So sorry. No, I made it. Yeah. So here, the cone must be in the valuation cone. So the cone must be here. So if we want to do the completion of x1, we have to take this half line. We can't take the color here. So it's the unique possible completion of x1. And in fact, it's the unique x1 embedding, non-trivial. So there is two embedding of x1. It's Q2 here and x1 itself, because we have only choice here and not here. Yes, that's what I wanted to say. Thank you.